Hello guys, this is Farhan from AlgosFromScratch, and I welcome all of you to this amazing YouTube playlist on building DistilBERT model from scratch using PyTorch. This is the second video of this playlist, and in this video we are going to cover the complete architecture of DistilBERT model. So this is the architectural overview, not the in-depth discussion of the architecture. So we will have just an overview of the overall architecture, how this architecture is, and how the data is passed through this architecture. Okay, so we will have in-depth discussions on each and every part of this architecture, as we will be developing each and every part from scratch using PyTorch. So this is just going to give you a big picture of this architecture, so you have an idea how this architecture works and what is the architecture that we are going to use. Okay, so starting with the first part, that is the input plus attention mask. So input and attention mask that we basically get from the tokenizer part of this model. So before this part, we will have this tokenizer layer where we will pass our input data, and that input data will be tokenized by the tokenizer, and we will have input IDs and attention mask. Okay, we will have our in-depth discussions on all of these, so don't worry, this is just the overview. Okay, then we pass those input IDs and attention mask to the embedding layer of the model. This embedding layer of the model basically is a giant lookup table with the rows equal to vocab size and these columns basically the dimension of each token. Okay, so we also add this embedding of the token with the positional encoding. Okay, so positional encoding is also a lookup table with all learnable parameters, where we have the number of rows equal to the maximum length of the input sequence. So in case if you have input sequence maximum length 128, so this will be 128 by 768. That is the dimension used here in the embedding layer as well. So this number is basically, you can change it. Okay, and whatever input maximum size you want to pass, you can change it. Okay, so next is when we pass this in these input IDs to the embedding layer, we get some output, and that output is basically the batch size, like how many sequences, how many sequences you have in your data. And we have 128, let's say, the maximum size of each sequence in that data, and the 768, let's say, the dimension size of each token in these sequences. Okay, so we will have 128 tokens in each sequence. Let's say we have here 2, so we will have 2 sentences or 2 input texts. Each input text will be represented with the help of 128 tokens, and each token will have 768 dimension. Okay, so we pass this embedding output to the transformer encoder part. This is the, you can say, heart of the architecture. Here we have 6 transformer blocks in just one major box. Okay, so this is this outer parent class basically contains 6 transformer blocks, and they are stacked like this one on top of another. Okay, so the output of one transformer block becomes the input of another transformer block. Okay, so this architecture contains 6 transformer blocks within this encoder, and within each transformer block we have all these 4 steps. Okay, so the first step is multi-head attention. Okay, So this multi-head attention is the step where basically we split our dimensions, like 768 dimensions, into equal number of heads. So each head carries its own dimension, and then within each head, like here we have 12 heads, and each head will carry the 64 dimension values of the token. Okay, so this multi-head attention will basically calculate attention scores, and we will have, by the end of each head, we will have some attention scores. Okay, we will then concatenate all the heads outputs, so we will have the complete output now again in the form of 768 dimension. Okay, so this is the multi-head attention part, you can say, in this overall transformer block. The next part is this add and normalize. Okay, in this add and normalize, what we do, the hidden state from the like passing the data to the before passing the data to the multi-head attention layer, we also pass it through this way. So the original input values, we carry them along, so we can later on add them with the attention output just after this multi-head attention block. Okay, then once we are out of this layer, we pass the output to a very important part of this overall transformer block, that is the feed forward neural network. Okay, so this feed forward neural network, we will cover this in detail, why we use this, why just not pass the attention scores directly out of the transformer block, why we need this specific architecture. So we will discuss it. Okay, the reason behind it. So in this, we kind of you can see here we have this 3078. So what we do, like from 768, we expand the span of dimensions to 3072. So okay, we will kind of cover this. We will discuss the reason behind this. Then we compress it back to the same dimension. Okay, this is what this feed forward neural network layer will be doing to the input values we get after this SA, that is self attention layer norm layer. Okay, so this is the one of the very important parts of this block. Then again, we get the output from the feed forward neural network, and we pass it to the output. We pass it to the layer normalization. Again, we repeat the same process. We add the hidden state to the feed forward neural network output, and we normalize it. Okay, so this is again the add and normalize layer. We repeat this process after both of these main parts. Okay, like multi-head attention, then add and normalize, then feed forward neural network, then multi-head attention. Okay, and this process of 4 steps repeat itself 6 times. So that is how we say that we have 6 transformer blocks within this encoder part. Okay, once we get the output after the 6th block, so we pass it to this layer, you can say. This is the concept where we extract the CLS token. Okay, we will discuss what the CLS token is, where does this come from. So we will discuss it. Okay, no worries. This CLS token, just remember that this is the very first token in every input. Okay, so we will take the very first input, that is the 0th index of every sequence. We'll pass it to the classification head. So this is the classification head. This head basically we change this head as per our requirement. The encoder part stay, but this classification part basically we change it, okay, as per our requirement. So in this specific architecture, the main architecture is till this point, you can say, but we will be adding this classification head as well. In this playlist, we will be working with such classification head where we will have three layers in this classification head. First one is pre-classifier. So this is a pre-classifier. We use ReLU activation function in it, and we just pass it with 768 dimension size and get the output of same dimension. We then apply some dropouts. We will discuss each and every part in our upcoming videos. Just focus on the overall architecture for now, okay? Then we pass it from the final classifier layer. This final classifier layer basically converts the 768 dimension to 3 logits. These 3 logits basically represents 3 different classes that we want to classify against our input text. So maybe let's say we have negative, we have positive, we have neutral. So these 3 classes, and against each class we get 1 logit, okay? Then we apply some softmax to convert these logits to probabilities, and finally we just get the output, okay? So this is going to be the overall architecture of this model we are going to work with. We will have complete in-depth discussions on each and every layer and each and every part of this architecture. The most important part of this architecture is this multi-head self-attention, and we will be doing even the mathematics behind it with some hand calculated values so you can understand it properly. We will understand how these 12 heads basically get executed parallelly with the help of GPUs. So just stay tuned, and we will discuss each and everything related to this architecture. First of all, in our next video, we are going to download the model from Hugging Face library, and then we will use the model with the help of Hugging Face library. We will fine-tune the model on some specific classification data, and then we will execute the trainer loop, and we will fine-tune our model. We will use it, we will test it, and after that we will then start our real journey of looking into the architectures of tokenizers, models, and then writing our custom classes in PyTorch, okay? So this is it for this video. I hope you enjoyed the lecture. I see you in the next lecture.